speaker is Jan Peters. He's full professor of Intelligent Autonomous System at the Technical University of Amsterdam and head of the Systems AI for Robot Learning Lab. He has significantly contributed in robot learning and motor skill acquisition, particularly using reinforcement learning and probabilistic movement representations. So, thank you.
Thank you, Ricardo, for the nice introduction. So let me first start out by saying I wanted to initially give a much broader talk because in the end, like nearly all we do in machine learning has a form of energy in there. Like even supervised learning has a form of energy in there, has entropy somewhere in there. You can view updates of models generically as energy updates. And when you do reinforcement learning, you actually can model everything as an exchange of energy between the environment and the agent. Now, I started preparing the talk and then I realized it would be really unfair to my students, and particularly two students whom I have highlighted here, Lukas Schulze and Michael Luther, who have been doing pretty amazing work. And so I'm going to give you a tiny outtake, but much more technical outtake of what we're doing, since we're using energy, of course, in model learning for control. And that story even has a very, very long background. Since, I mean, like all of you guys are aware, we need models, representative models, for simulation, for state estimation, control, planning, and we won't get away with that without them. And, well, quite clearly, that's something where we end up having to deal with when we're dealing with learning, since not everything can be just obtained by white box methods. It's, well, on the one hand, white box methods, as long as we have good physical insight, can be extremely powerful. Whether we take CAD models, disassemble robots, measure every part, in the end, this can either be time-consuming, it could be incomplete. System identification, we all know, is actually a non-convex problem, and you need to bring in some additional biases to make it work well, whether that is regularizing it towards the CAD data, as I believe you guys at DLR are still doing. It requires proper persistent excitation, since otherwise you will have an impoverished signal, and often we get even there physically implausible solutions that don't generalize that well. And we need all this prior knowledge in order about the system, which might fail. Now, the next thing, of course, has been proposed about as long as there are neural networks around. So the earliest reference I could find of learning everything with the black box method from data, the earliest reference to that kind of model learning that I could find, it was in the 1960s. So where people learned a single degree of freedom system and learned a model of that. Well, big surprise, people are still doing that. Now, that brings me to, of course, on the one hand, this is really great, no prior knowledge required, but it doesn't generalize. If you violate physics, you can violate it so badly, you cannot integrate it. And we will keep reinventing that, of course, and keep redoing that in the area of machine learning, but it's a really bad thing to do. And just to give you an example of how bad, let me explain in you one story from when I started as a group leader at Max Planck. I was just a postdoc, just graduated, and the Max Planck director said, "Jan, impress me." And well, I wanted to impress him, so I learned a forward model, so a physics model, and then did a model-based reinforcement learning method on top. From a reinforcement learning point of view, that was state-of-the-art for being fast, and it seemed like a good way to impress people. Simulation, everything looked perfect. Then I ran it on the real system without any safeguards, and it made bang! Right? It became unstable. Right with the joint limits, I had to go to my boss and say, please, you've given me 150K to start and buy a Barrett RAM, now you have to give me another 10K to repair it. So not the best start when you're starting a new group. But at the same time, it made me really look into what that black box model had learned. So the black box model was much better than the classical physics model. And it was done back then with a GP, which was the state of the art, and it had just basically violated physics. And since then, I think it has become to me really important that whenever I want to learn a model, I have to figure out how to make it physically consistent and safe, such that my reinforcement learning method or if you want to use any kind of optimal control method or MPC method, the same would obviously happen, is safe in conjunction with a learning approach. And for that reason, I think we really have to focus on gray box models, because we want to be better than anything which physics can deliver, but at the same time we want to preserve the physical consistency, the interpretability, we want to generalize better, and ideally we want to put in very, very mild assumptions. So for example, you could put in differential Newton-Euler as an assumption, or you could put in Langrangian and Hamiltonian mechanics as an assumption. And if you're really, really lucky, you need very little prior knowledge regarding your dynamics and your kinematics. So let's have a quick look here. Here you have basically the taxonomy of models. On the very left you see what we did before we did system identification, take the robot apart, measure everything, and we get everything beautiful, consistently with physics, with only the problem that there are things like friction, like actuator dynamics, and when things bend and are impossible to measure, we get a really, really big problem. You can make it a bit easier, get some of the work away by system identification, but the opposite extreme of black box modeling is without assumptions is actually really, really bad thing. And you don't even get all the kinds of models in there, because you get only forward and inverse models, and in many cases energy models may actually be much, much superior. So for that reason, we have been pushing for about quite a few years to use explicit physics principle even in representation learning, while trying to build upon the flexibility which you can obtain from learning systems. In that way, if you do it right, you get physical plausibility. You're not gonna look as bad to your boss as I did back a few years ago. You get interpretability because you can actually extract relevant physical components, and in a way, you can even learn things for which you don't have a learning signal, right? We cannot observe energy. Energy is in the end a physical construct from which we can derive a lot, but we cannot observe it. And for that reason, we need to indirectly incorporate it also into the learning approaches. And then we of course want to have energy models, inverse models, forward models, operator models, models where there is something which we cannot model, like a beam which is bending as a link, and all of this ideally in there. And one of the ways of doing this really well is to, of course, hard code basically into your neural network that it can only learn Langrangian dynamics, mechanics. And if you do so, you actually get all the kinds of output you would like to have. So you can get an inverse model if you want to do model-based control. You can get a forward model if you want to build a simulator, and you can get energy if you want to get an energy-based controller, for example. And what is even cool, and maybe here I should really walk there and quickly highlight this, I'm going to put a red arrow around it. But what's really, really cool is that if you do this with what we call the DLAN architecture, you actually get two kinds of learning signals, and combined, they're really, really good learning signals. I will yell without a microphone in a moment.
Since you have the obvious supervised learning signal, but you also have a not so obvious signal, which helps you though to get a much better physical consistency. Only by combining the two, you get really good performance.
It's going to be the only time, but thanks. And obviously, if you take a simple simulated robot, everything works out of the shelf. But as they told me during my undergraduate when I worked at DLR, never believe anybody who shows you simulations. You always have to see it on the real system. So showing that learning works in simulation is at best a proof of concept that your concept is correct and that you can code. But we can actually show it on a Barrett-Wemb robot. This is a Barrett-Wemb robot which only had motor side joint encoders. So there is a flexibility in there of the cable drives which can give you an end effector error of 2 centimeters. That's one of the reasons why the Barrett-Wemb is only useful for either haptic-based things or if you do things with learning. because if you have to use classical approaches, you have too many unmodeled components and errors in there. But we can actually get really high tracking performance then on completely the motor side. And if you look at the controls and compare it now to supervised learning methods, so the standard off-the-shelf feed-forward neural network, deep neural network, of course, by overfitting to the data set, a physically non-plausible neural network can do much better if you test it again on the same class of trajectories. But if you just move to a different set of trajectories, different set of cosines, you can directly see that you need that physics gets violated by the neural network by just these mild changes, and that the physically plausible approach works much better. Then you can employ the energy which you're getting out of these Langrangian neural networks, and you can apply that directly to control under-actuated systems. In this case, for example, pendulums with one passive and one active joint. And you can close the loop, just give it an energy-based control law completely based upon the Langrangian neural networks. And this here is just a card-pull system, so the most basic setup where you can show these things. And of course, this one you can make work with an analytical model. This one you can make work with a system identification because it is so straightforward. Already for the Furuta pendulum, which in the end is just includes, this Furuta pendulum is very short, so it's just 2 centimeters. So you're always deep into the noise. And for that reason, the system identification actually fails. And you can even show that this is partially a bandwidth problem. That all the off-the-shelf system identifications methods cannot cope with that kind of data in there. And my student, he tried really hard. That's Michael Luthersberg still, who's now heading a group at Boston Dynamics. Here you can see the energy landscape together with the trajectories resulting from it. And you notice that, yes, it looks different, but in the end, it is as it was to be expected from a physical component. Now, this is all nice, but the first thing as a real roboticist, which you have to say is, well, what do you do if you actually use the robot? Right? If you want to use a robot, you want to attach a weight to it, and then your black box approach should be completely useless. Right? That's the first thing I would at least. I used to say always to the MLP people, and then I had this luck of having Lucas, who's actually in the audience here, who immediately said like, well, why don't we figure out how to learn this? In order to do this, he took the nominal model, which you can always learn as a first solution. And in addition to that, he figured out that we can condition on the context, denoted by Z here, and then you would automatically, of course, could learn a model if you have the right kind of context formulation, which would enable similar behavior. And well, context is for us, of course, then really powerful, because with the context we can now create trajectory statistics, for example, using a long-term, short-term neural network. And with these trajectory histories in there do enable us to cope with both things which are flexible, as well, like something which isn't perfectly attached, for example, or even a flexible link between 2 joints, and deal with the trajectory statistics as if they were another variable in our dynamics model. And Lucas first tried this in simulation, and it worked out there, and then he did it with it actually transferred zero shot also to the real system, where here you see this, these dumbbells are not perfectly connected, and you get here you see the performance of the nominal MPC as well as his Cadillac architecture, and in comparison you see an EKF, extended Kalman filter with the MPC, and the tracking error is significantly less with the Cadillac architecture based on the Langrangian neural networks. And here's a similar task with a pick and place, where one of the dumbbells is picked up, again on a flexible connection, and then the other dumbbell is also picked up, and again the tracking error reduction is quite significant in comparison to just using an analytical approach here. So, and Luca's big aim right now is to go for obviously floating-based systems, since that's where we have quite a few humanoids now in our lab, we have quite a few quadrupeds in our lab, and one of our goals is to always have this on have everything run on multiple robot systems, even when we are talking multiple humanoids, multiple quadrupeds, and he's done a pretty good job by focusing floating-based systems with it, and has figured out how to exploit the fact that something which initially appears really hard, for having a non-fixed base, how we can use this in, how we can use the structure that there are in the end quite a lot of zeros here in the lower triangle, and what he ended up doing is what he ended up doing, realizing that there is a stationary component with stationary masses in there, which wouldn't change, some skew symmetric coupling, and compositional rotational energy. And if you bring all of this together and use this triangular structure on the zeros, you get an intuitively nice looking inertia matrix with the components that can be nicely interpreted, and which actually also facilitate learning them. And because now we can can decompose our inertia matrix into a model which is used twice by Cholesky factorization, and which was originally proposed by Roy Featherstone, which then gives us something which is incredibly sparse in the number of elements that we actually have to learn. So it turns out that in this case, Langrangian mechanics needs fewer parameters than actually Newtonian mechanics, and that's a huge advantage, of course, for a learning system, where of any learning or system identification system, and it works very well for learning floating base systems with what we now call the PHLAN architecture, the floating base deep Lagrangian neural networks, and where we now have multiple multilayer perceptrons which all feed into this L matrix as well as a potential energy term. And from that we can get, for example, a good inverse model as well as energy models and forward models. And Lucas verified this in simulation on the GoToLink Talos, and he verified it already on several real robots, including a Talos, a Spot with an arm, and an IQ Real 2. For all of these, he had torque sensing, so he can actually do proper evaluations, and we still hope that he's also going to show it on our G1 and H1 in the foreseeable future. And here you see how good the performance actually is, and it's surprisingly good at predicting torques, and you can even again evaluate the different parts. The gravity part here just has two little arrow to really see this properly. Now here the Coriolis forces have two little variants. This is the reason why it looks like there was a large error, but when you look at the scales, you recognize that the error is actually not very long, very big. It's just that the terms are very small. And again, this nicely verifies in simulation on the real robot, but you can see similar behavior. So, quick summary, and I apologize, somehow from the export from the web-based slides to the PowerPoint slides, things have overlapped. So we can enforcing physics consistency enables us to improve learning and generalization of learned models. Incorporating structure is very, very powerful, since we can get energy-based control laws, we can do classical control and with learned models, we can do MPC with learned models, we can get good simulators with the learned models, and we will need more and more of that, because we will never get a digital twin of the whole world. We will at best get a digital twin for some situations, and the flexibility of neural networks on the one hand allows us to get better performance And we can use this now, thanks to Luca's work, across multiple contexts. And he showed that this actually works really well for simulation and nominal robot models. And even cooler for floating-based systems, this works by using these composite spatial inertia and the branch-induced sparsity. With that, I'm close, and thank you for your attention.
Thank you.
And computers, please get up so that people see you, since I've been talking so much about it.
Thank you. So we have already some questions. So yeah.
Thank you, Jan. Great work. Now, at the beginning, you mentioned it's a disadvantage for the identification persistent excitation. I mean, you have this if you do online. Otherwise, you just need to excite your whole workspace.
Yes.
But you need that for the network as well, I assume. So my question is, how do you have any statement about the amount of training data you need? I mean, in order to identify somewhere in the workspace, you need to go there. So is there a difference in depending on how much structure you put on the number of data and how this correlates to training performance?
Yes, there's actually a fundamental difference. And you don't even need to look at this work. You can go quite a bit back to my student Duinuin Tom, who already showed 15 years ago that if you the big advantage of learning-based method at that time based on kernels, which also have the squared form of the inertia term here, by the way, is that you would locally always have better performance and you would not actually need persistent excitation that crazily because your parameters had no global, or didn't have such a big global effect. While if you're doing system identification where you have very parsimonious lumped parameters, it matters a lot of what kind of exploration you do. So if I do a lot of training data, so in table tennis, for example, we did system identification, and we initially thought we could just take we had to take all of the workspace equally. That gave us actually a really bad model because, well, we didn't have enough excitation at where we would hit the ball. And on the one hand, you need the breadth if you have lumped parameters in order to get the parameter class right. On the other hand, you would also need then local exploration to get the performance right. For the learned approaches, on the other hand, we can have them if we make the network big enough, or if we take a Gaussian process, a kernel-based model, with the data set big enough. In this case, we actually don't have the same problems as you have in system identification. That's a huge difference between both fields.
But if you want to go global, I mean, I agree to your point that you say if I have a specific task, I would like to do identification of a model with high precision in the area of my task, right? With my hands, I manipulate in front, not in the back of my, I don't need a model for that. So what you say is that because the models, the parameters have local influence, you can learn good local models with less data. That's what you say. And probably if you go to global, they would approach, but what you say is in most cases you don't need global models.
There is always an exploitation dilemma, right? Whether we do system identification or whether we do learning. But there's a huge difference because in system identification, if you do it properly, you have to ensure you basically will have non-convex combinations that don't add up. While, for example, the Langrangian neural networks don't run into this problem. For that reason, even the physics components learned in the Langrangian Langrangian neural networks generalize sometimes better than if you were using the same fixed basis functions, which we can extract the basis functions from the mechanical model. It turns out the basis functions from the mechanical model are more prone to be problematic there than if you use flexible basis functions.
That's interesting. So maybe we have an opportunity to do something together with Lucas and so on. I would like to explore that on some of our models. Great.
Be fantastic.
Thank you.
Next. Okay, we go with it.
Thank you so much for the nice presentation. I want to ask if the uncertainty is included somehow in the learning dynamics model, because I assume if it's considered well, that will improve the quality of the learning model.
In this work, we didn't do that. In previous work, where we did, for example, GP-based model learning, then also when we did semi-analytic GP-based model learning, which was much more simple than what we're doing now, we did include it, and of course, having uncertainty always helps. I also still think there's something for control where we should be using the uncertainty of learned models much more, because it would give us a free way of accessing stiffness, yes, and getting a different way of even thinking about stiffness, which is much more human-like. So the human stiffen, as for example Etienne Bourdet many years back showed very nicely, even also as Cavado showed, there's a lot of connection for human movement between stiffness and uncertainty, and currently we have no good mechanism, and this should come out of learned models much better. But we haven't done this in the context of Langrangian neural networks yet. It would require Bayesian Langrangian neural networks, and I think we're just planting an idea into Luca's mind already here.
Any plan to do that soon? Okay, thank you.
Yeah, it's a very attractive and convincing approach. There are situations where the dynamics and environment is not energy conservative, it's dissipative, even strongly dissipative, so that part dominates the behavior. Do you see that this paradigm is applicable there as well?
So far we've only, of course, observed this when it came to stiction, for example, after friction. And in these cases, you can either create a handcrafted model, or you basically try to focus on these situations and learn some additional terms very explicitly. So yes, absolutely, these things exist, and they still, well, at the moment we have more or less manual treatment of these situations. So far we can deal with them still.
We have time for one last question.
Hi, thanks for the really interesting presentation. I have only just a curiosity or a question. You showed that the learned energy landscape is not, of course, exactly as the, let's say, the model-based one.
Mm-hmm.
And then
remember they're both models, right, in the end.
Okay.
The physical model, which looks so beautiful, is of course as unreal as the data-driven one. We actually don't know which one is,
of course,
really describing the physics situation better, right?
Yes. Now my question is, if you apply such methodology to an energy shaping approach, like for instance we told with Federico before IDA PPC, which is an energy shaping approach, in that case you have to solve some matching equation, but the insurance that the closed loop system is passive, or better, the insurance that the closed loop system is a Porta-Miltonian system says to you that the system is passive too. Now, since you are not sure that your system is exactly the final one, a Porta-Miltonian one, how can you, let's say, ensure that passivity is fulfilled?
I think about that, I think we have to take that discussion off.
Because
that's a really interesting discussion. Obviously, you could create additional terms, like people have always been doing, but this is passivity and learned representations. That's a complete second story to talk about.
Okay. Thanks.
Okay, thank you. Thank you very much. Okay, we have the coffee break, and we will meet again at 15. Okay.